Hello. So today I'm going to do the presentation in this way by talking over the PowerPoint and recording it for you, because I figure you can then go back and watch this at any point. You can rewind any of it, and we've not got any of those problems with waiting for people to be able to log on and getting kicked out and so on. So I'm hoping this won't be too long, although there is a fair bit to get through, so bear with me. Remember you looked at the Doppler equation, so I'm just going back a little bit here because this is going to be important for understanding what Hubble did. And you've read a bit about that, of course, yesterday, so you should be reasonably on top of this. Hubble used the Doppler equation because he wanted to know the speed at which different galaxies or different stars in galaxies were moving away from the Earth. So this equation here, remember, enables us to work out if we know the wavelength that a certain part of the spectra coming from a star should be at, and we can see where it's been shifted to, then that will enable us to work out the speed that the galaxy is moving away from us at. It's a relative speed, of course, because we know the speed of light. That doesn't change. Now, how do we know this bit here, that the wavelength has shifted? Well, remember there are certain signatures we look for in the spectra from stars, such as the Balmer series that show that hydrogen is present. It has a certain fingerprint. The lines are spaced and make a certain pattern. If we see that pattern and we know it's hydrogen because we've got those particular lines and they're particularly spaced, but they're not in the right place on the spectrum, so they've been moved to the left or right, so maybe the lines make this pattern, but actually we're seeing them over here, okay, they've been shifted this way, then we can work out that change in wavelength here and use the speed of light to work out the velocity. So that's the idea. So, just a little bit more about this. Here is something stationary. The lines are where they should be. This line here is called the hydrogen alpha line. It's just one of the lines that we look for. Don't worry too much about the name of it, but it's part of this series of hydrogen lines here. So this one on the right is the hydrogen alpha. If a star were not moving, which of course is not the case with any of them, other than our sun relative to us, then it is where it is at the top. However, if that star is moving away from us, which is what receding means, similarly to the way in which my hair is moving away from my forehead, it's receding, then we get a redshift. That's where the wavelength is stretched, and we can see that the hydrogen alpha line has moved over to the right. If the star were moving towards us, which we would call approaching, unlikely unless it's in a galaxy close to us, then we could get a relative movement where it's getting closer, but of course in general everything in the universe is moving away. If it were moving towards us, we'd expect it to shift this time to the left. And this question here, which you could feel free to pause and try this. I'm not going to explain the whole thing, so I don't want it to be too long. But essentially, we're given the wavelength of one of the hydrogen lines measured in the lab using a spectroscope or something. But when we look at this line coming from a star, it's now got a slightly different wavelength. We're going to put it into that equation, as I mentioned before, change in wavelength over wavelength. That's going to give us speed of the movement of the star over the speed of light, rearrange because we know the speed of light, and we work out that this is the speed that the star is moving at. So like I say, pause that if you need to look at that in more detail. So that's a relatively easy application, but actually a lot of the stars we look at are binary stars, as mentioned the other day. The two are orbiting, well, we often say around each other, it says around each other here, but actually they're orbiting a common centre of mass. So if you've got two stars here, they're actually orbiting a point there. that one is going around that point, and this one is also going around that point. It has the effect of them looking as though they're going around each other. So a lot of the stars are like this, and this makes the redshift well, a little more complicated, but actually a little more useful as well. Because we might not be able to resolve these stars, we might not actually be able to see them as two separate stars using our telescope. However, as they orbit each other, of course, it will affect the absorption spectra. When we see this happening, we call it a spectroscopic binary. So it's still a binary star system, but it's one that we've identified because we can't resolve the stars, but we can see the spectra coming from the star changing. I'm going to skip this one actually because there's a more useful one later on. This one here. We've got two stars, star A, star B. Star A is slightly larger here, and that will come into play when we look at this. You can see that we're looking from over here. So at the moment, from that point, star B appears to be moving towards us and star A is moving away. Let's have a look what happens here. So let's just bring all this up actually because it will be easier. So at this starting point, the lines that we've drawn on here, the green lines and the pink lines, they represent the H alpha line. They're only green and pink because we've done star A and B in green and pink. They are the same element, hydrogen. And we can see from star A it's been redshifted from where it should be. Where it should be is this line down here. It's been redshifted because the green star is moving away from us. It's been relatively blue shifted because the pink star is moving towards us. So we've got some redshift and some blue shift going on. What we actually see is the combined spectra here. Remember, we're looking at this as just one blob of light in the sky, but we bizarrely get two hydrogen lines, both in the wrong place. One too far over to the right, one too far over to the left. It doesn't stay stationary either. If we watch this over a period of time, and it could be a very long period of time, it could be years, depending on the time period of the orbit of these stars. If we keep watching it, as the stars move, you can see, I'll just go back, they've just moved from that position to that position. Look what happened, I'll do it again, to the lines. Okay, they are still red shifted for star A and blue shifted for star B, but not as much. Then they come into this position here, and because they are both in our line of sight, there's no shift. They start to move away, and now the one that was blue shifted is red shifted. The one that was red shifted is blue shifted. You get the idea. So I'm just going to actually scroll through this a few times. You see those lines moving, and you can go back and play this again and just see how the movement of those lines relates to the movement of the stars. Okay. In this example, star A is more massive than star B. Well, we can see that because we've drawn a more massive picture of star A, but how would you tell it from the combined spectra here? Well, because the light from star B is actually being shifted more. Now, if you think about it, think about what you know about things in circular motion. Okay, the fact that the star B is lighter means it is going to be moving faster and have a bigger orbit than star A. So you can tell that because it's shifted more. So another question you may get, and again, feel free to pause and have a go at this, pause the video here, try and work it out, and then press play again when you think you have that. This is slightly more complicated than the last question. It talks about the hydrogen alpha spectral line again. It tells us that it merges once every 5.3 years. That means those lines are in the correct place from both stars every 5.3 years. Think about the diagram we just looked at. That means they are in our line of sight, one behind the other. We're also told where hydrogen alpha should be, again from a laboratory measurement. And we're told the maximum amount that it is shifted. Okay, so we've got 3 bits of info there. We want the orbital speed of the stars and the radius of their mutual orbit. They are both orbiting a common centre of mass, remember. And it just reminds us down here that the speed of light is 300,000 kilometres per second, or 3 times 10 to the 8 metres per second. There is our equation. We've used it once, you're going to use it again. What we're doing is putting all the detail we know in, the known wavelength of the hydrogen alpha line, the difference, so we're going to have to work out that difference, okay, it's the difference between the 2 numbers at the top, the maximum and where it should be, and we're going to put the speed of light in here. Now we've actually kept that in kilometres, but that doesn't matter because kilometres per second over here as well means that that doesn't matter to us as long as that answer's okay. So we're putting the speed of light in, we're putting our difference in, and there's the difference there, and we're putting our known value in there, and we then come out with this speed. So that's the first bit done, orbital speed. Now the merging of the line occurs every half period. Think about it, one star goes behind the other every half a complete rotation, doesn't it? So that means that the time period is actually double the 5.3 up here. What do we know about the links, time periods, radiuses and speeds around a circle? We've done this equation loads of times. 2 pi r over the time period. This is just distance over time. Distance around a circle over time period for that circular motion. Rearranging that to get r as the subject, we get a value for the radius of 3.7 times 10 to the 13 metres. So hopefully some of you paused that and got that correct. Moving on. If the stars are of different masses, okay, this is just a recap. Okay, I've already explained this to you. We can see clearly here that one of these stars is shifting more than the other over here. So the one with the smaller shift is the more massive star. Just remember that. The one with the smaller shift is the star with the higher mass. So now we're on to Hubble. This is what I asked you to read yesterday. So what did Hubble do? He plotted the amount of redshift, and he was using the equation we just used, okay, the Doppler equation. So he was looking at the spectra, he was identifying certain lines, and he was seeing how much they'd been shifted from where they should be. From that, he could work out the speed those galaxies were travelling at. Now the thing is, he plotted that speed against their distance from us. So there is a missing piece of information here. And I know we've spoken about this a lot. It's very complicated. How do we know how far away things are? Well, we could use parallax angle, but it only really works for things pretty close to us. And what he would have used would have been standard candles. We've spoken about that as well. They are things in the universe that we can see and identify and know that they have a certain absolute magnitude. So we know they're a certain brightness. And when we know that and we see how bright they appear to be, we can work out how far away they are. Go back and remind yourself if you can't remember that. Things such as certain types of supernova, things such as the variable stars, the stars that pulsate with a regular time period, and that tells us about their magnitude. They're called Cepheid variables. That will be coming up soon as well. So there are a few things that if he spotted them in a galaxy, they would tell him how far away that galaxy was. Now this was in the early days of doing this stuff, so it wasn't particularly accurate at that point. And that's why we've got the word rough here. when he plotted the speeds of these galaxies against how far away they were, he got something like this. Now, that is a nightmare of a line of best fit because those points are all over the shop, okay? And it's actually astonishing that he got close to a value for the Hubble constant. Bear with me, we'll explain what that is. But it's astonishing that he got close to a value that we still think is correct because really his points were pretty bad. There's a picture of him. Looks a little bit like Robert De Niro. Pretty cool picture. So he plotted this. What does this straight line say then? Even if he's got this straight line kind of wrong in terms of its gradient, we can see there is a trend here, no matter how rough. And the trend is that the further away these stars are, or the further away these galaxies are, sorry, the more they appear to be redshifted. Right, well, if they're redshifted more, that means they are moving more quickly. So he's suggesting that the further away things are, the more quickly they are moving away from us. And of course, if you are awake and switched on, you should realise that what that tells us is that the universe is not just expanding because things are moving away, but it's actually accelerating in its expansion. So the expansion is getting faster. There's some more data on that similar graph. So what Hubble's law says in words is that the speed of recession of a galaxy is proportional to the distance to the galaxy. So with any proportionality, we can make that an equation by putting a constant in. The constant that links the speed and the distance is now known as the Hubble constant. Let's just flick back. It would be the gradient of that graph. And the Hubble constant, and this does change, and it changes fairly regularly, you know, on a yearly basis almost. But it's something like 65 kilometers per second per megaparsec. Okay, so for every megaparsec away you get, the star travels another 65,000 meters per second quicker. Pretty astonishing stuff. Use the value you're given in the question or on your formula sheet because you will find different values all over the place, but they are all around that value. Remember, a megaparsec can be converted using all the data you've got in your astrophysics section of the formula sheet or anything you can find online. It's about 3.26 million light years. Hubble's law does not work with some nearby galaxies which are approaching us, where we talked about the fact that some nearby ones may be approaching us. That may come up in a question where they're trying to catch you out, maybe, as to why you've not got the data you're expecting. So a question, again, feel free to pause. Calculate the distance in light years to a galaxy if its recessional velocity is 10% the speed of light. So what we are saying is it's moving away from us at a speed of 10% of 3 times 10 to the 8. Okay, and we've got a parsec there in light years as well to help us. So the Hubble equation, really very simple, isn't it? We're just going to put in V as being 10% of the speed of light. Pardon me. We are going to use our Hubble constant here. And that will enable us to calculate D. And the distance we get is initially this one down here, okay? Mega light years. Sorry, I said initially it was that one. What I actually meant to say was initially it was this one. We get it in megaparsec, sorry, and then we converted it into light years. It didn't actually ask in the question for the answer in light years. It could ask for you to leave it in megaparsecs. I suppose if they're being really nasty, they could ask for it in any unit of distance that they wish, but they are the two most likely ones. By the way, if it is 1.5 billion light years, that's the distance light travels in 1.5 billion years, then that's already suggesting that the universe is pretty old. I can't actually see the top of this slide because my menu is in the way. The expansion of the universe. So Hubble's law tells us galaxies are moving away. It also tells us that they move faster the further away they are. That means the universe is expanding. Now, one of the ways you can model this, if you're really bored today, to try and get your head round how everything can be moving away from everything else, because remember, we are not the centre of the universe. It's not like we're in the middle and everything's moving away from us. You can be anywhere in the universe and everything is moving away from you. Pretty difficult to get your head round. If you're bored, get a balloon, draw a few galaxies on that balloon, inflate it first I should say, draw a few galaxies on that, inflate it just a little bit in various places, and you see then as you inflate it more, every galaxy on that balloon moves away from every other galaxy, okay? And that's a bit like the universe. The universe is, in this analogy, the outside skin of the balloon, if you like. The centre of the balloon is nothingness. Outside of the balloon is nothingness. Okay, it doesn't exist. The universe can be thought to be like the outside skin of that balloon, where everything on that skin moves away from everything else. And there is the balloon expanding. Pretty difficult to draw on a PowerPoint, but I'm sure you get the idea. By the way, if you do want to do that, you can find instructions and YouTube videos about doing that experiment and actually taking a measurement of the Hubble constant by doing that. Believe it or not, you can do it with a balloon. So again, if you're bored, maybe have a go at that. Now, here's the really cool thing about the Hubble constant is that... How do I get my pen stuff back up? I'm not sure. I'm actually just making a mess of the screen here. I seem to have lost the ability to go back. Never mind. We can estimate the age of the universe actually by using the Hubble constant. How can we do that? Well, the Hubble constant tells us the speed of a galaxy increases by 65 kilometers per second for every megaparsec. So for a galaxy to actually be moving at the speed of light, okay, because that's the fastest a galaxy could be, nothing can move faster than the speed of light. If we actually put these numbers in to the Hubble equation, we find out that it is 15 billion light years away. So we've just put that into the Hubble equation. Galaxies cannot travel at the speed of light, okay? It's impossible. Actually, anything with mass is unable to travel at the speed of light because some of the stuff that Einstein did that we're not going to mention on relativity tells us that their mass will increase massively as they approach the speed of light. So this puts a limit on the age of the universe, okay? It cannot be more than 15 billion light years. Okay, so rather than people say this is giving it an age, I suppose it's giving it a maximum age. Okay, a maximum age. So the universe must be less than 15 billion years old based on that sort of logic and calculation. The current greatest length of time observed is about 13.5. Okay, so that's based on stars that we can actually see and measure the speed of, moving incredibly fast, but not moving at the speed of light. So, As can be seen in the above calculation, the maximum size of the universe, d, can be given by c over h. What does this mean? Right, this just means that what we were doing there was plotting the speed of light. We were taking the speed of light and we were dividing it by the Hubble constant to get that sort of upper age limit. But we know that distance is equal to speed multiplied by time. And what we're getting here is a distance, okay, the maximum size of the universe, the maximum distance it's expanded. If that's equal to speed multiplied by time, okay, for a galaxy travelling at a speed, the speed of light, okay, we can deduce from that, let's just bring all of this up and then you can sort of pause this and have a look, because this is slightly confusing, this bit here. We can deduce from that if distance is speed multiplied by time, then actually 1 over the Hubble constant gives us a time. Okay, 1 over the Hubble constant gives us time. So you may just want to look over that again. All we've done there is put in our, let me just try and highlight the correct bit with my fat finger, speed multiplied by time there. Okay, so same as we've got up here, but instead of d, we've just got speed multiplied by time to give us a distance. And time is what we want here. Time is the age of the universe. Now you see, if you want to get t on its own, c is going to cancel and you're going to end up with 1 over h. So this seems like quite an easy question if you were to get this, because it seems like they're just, if they're going to ask you to estimate the age of the universe, asking you to do 1 divided by the Hubble constant. But it's not quite as straightforward as it seems, because remember, the Hubble constant has this really awkward unit. Where is it on here? So this is a measurement of the Hubble constant. It's a different one to the one that Hubble got, okay? It changes. But look at the unit, kilometres per second per megaparsec. So doing 1 over that is not going to give us a particularly nice value. What we want is a value that is in seconds, or a value that is in years ultimately. So what we've done here is we've taken, and again, pause if you need to, I don't want this video to be too long, it's already too long. We've been told up here that it was measured, the Hubble constant, to be this. However, there was an uncertainty of this much. So if we take that uncertainty, because it was a plus or minus uncertainty, away to get the minimum value of the Hubble constant, we end up with this. We want to do 1 over that, and that gives us this. Now that's not, or it doesn't look like it, is the age of the universe, and that's because it's in a very strange unit, megaparsec second kilometres, or seconds per kilometre. So we can start converting all this stuff to actually get this into seconds and years. For a start, a megaparsec is this many kilometres. So we now have kilometres on the top because we've replaced our megaparsecs with kilometres, and this is all per kilometre anyway. So in actual fact, what we end up with here is a value in seconds, because the kilometres disappear. When we've got it in seconds, we can change it into years. So see if you can do that. Take any value of the Hubble constant and do 1 over that and try to get your answer in seconds. It should be around 14 billion years, or 14,000 million, which is a slightly strange way of putting it, as they've done here. So make sure you can do that. A couple more things that were mentioned on the video you watched today. Supporting evidence for the Big Bang. Hubble's law is one of the pieces of evidence. The questions you're going to get are going to be along the lines of provide, what pieces of evidence were there or are there that support the Big Bang. Hubble's law is one of them. And actually, it wasn't really called the Big Bang theory. Somebody on a radio interview referred to it as a Big Bang. They were actually being a bit derogatory and making out that it was a ridiculous idea, but it just stuck ever since. So that's one piece of evidence. The other is cosmic microwave background radiation. This is radiation that we think is massively redshifted radiation from the moment of the Big Bang. Essentially, it's everywhere, it's coming from every direction, and it's at the right frequency we would expect based on our models of when the Big Bang occurred and how much it would be redshifted by. That comes from every direction. I'm just going to skip some of this. You can always pause this and read it, but this is background that you absolutely do not need to learn. This is just showing the gradual redshifting of that. That's actually the telescope that received it. And there is a map of the cosmic microwave background radiation that was received that gave that proof. So far we've got Hubble law, we've got the cosmic microwave background radiation, and our other piece of evidence is the relative abundance of hydrogen to helium in the universe. What do we mean by abundance? We mean how much of it is there. So there's a certain ratio of hydrogen to helium that was predicted would be the case if the Big Bang had happened as it did. Now, the Big Bang is another lesson. We need to do more detail, but essentially the predicted ratio is about 4:1, 4 hydrogens to 1 helium. And this kind of makes me laugh because the measured ratio is 3:1, which I wouldn't say is that much in line with 4:1. But still, as you can imagine, this is far more complicated than we are boiling it down to. You are expecting in a question to simply list these things. The evidence is Hubble's law. It is the relative abundance of hydrogen to helium. It is the cosmic microwave background radiation. And that brings us to the end. Now you've got a nice view of my desktop by the looks of it. So I am off to play some Uno down there. Have a great day. Any questions on that, you can leave comments on the video. I will try to enable comments on YouTube, and then I can reply to those comments. Or, if it's easier, email me and do it that way. Other information about what you need to do today is in the email I sent you. So have a good one. Bye-bye.